So the purpose of today's class is to talk about the postulates of quantum theory. And I will focus especially on the quantum bit, but I will say the postulates in general for finite dimensional spaces. But I'll focus the examples on the quantum bit, and then we will see other different systems later. Okay. Okay, so the bibliography for today's class, there are two books that I recommend where you can find exactly what I'm going to say here. First, this book that we wrote for undergrad mathematicians is chapter 6 and 7, but this is only in Portuguese. And the Bible of Quantum Information, which is this book by Nielsen Schwang. You can find it online, like the PDF. It's just Google it, you'll find the PDF. And chapter 1 is like a overview and introduction to quantum information. I highly recommend that you read it. And chapter 2 starts with the basic foundations that we need to study any topic in quantum information. What I'm going to say today goes from section 2.1, entire section 2.1, and up to subsection 2.2.5 of section 2.2. Okay. If you have trouble finding the book, just let me know. You can always reach me through this email here. I generally take a long time to reply, but you keep sending and eventually I will reply. I'm trying to be a better person and reply quicker. And you can also WhatsApp me. Benjamin and Lucas have my phone, so it's easier. Okay. I am trying to write lecture notes, but I will not commit to that because it takes a while, but if possible, I will provide that to you. And also these slides, I will send them to you after the class, okay? Okay, so to talk about a quantum system, remember that I'm almost a mathematician. From the perspective of the physicists, sometimes they see me as a mathematician, so I'll focus on the mathematics, especially in this class. So to describe a physical system, we need a few basic ingredients. The first one is what we call a state, which is the basic mathematics object that gives us information about how that system was prepared. So the first postulate we are talking about here is about the space. In quantum theory, we associate states with vectors, like we start associating states with vectors in what we call a Hilbert space, which is a vector space with a few special properties. First, we will only consider finite dimensional spaces. So you don't need to actually worry about what this notion of Hilbert space is, but later if we're going to talk about continuous variable systems in which this space has infinite dimension, then we need to worry about it. But for now, it's just a vector space with complex entries in the vectors. And this space is what we call the state space of this system. And it's the set from which we will take these objects that tells us how the system was prepared. Okay, the state of the system itself is a normalized vector in its state space. Normalization comes from the probabilistic interpretation that we give to this vector, which we'll talk about later. So for now, you just think that it is a vector in some vector space. Since we are dealing with finite dimensions, it is just a vector that can be written as a column or a row matrix with a finite number of entries, okay? And these entries are complex numbers. Later, we will talk about infinite dimensional systems, which in general we call continuous variable systems. We have a lot of people here working with this kind of system, so it's important to talk about it as well. But that's what we need to keep in mind for now. So we just imagine that we have a vector in a complex vector space of some dimension. That let me just keep the notation here. So here we have dimension D, and normalization means that the inner product of the vector with itself needs to be equal to 1. This comes from probabilistic interpretation of the state vector that we will see when we talk about postulate 2, okay? So what we call the quantum bit is just a system that can be described with a two-dimensional Hilbert space. So the Hilbert space of the quantum bit is C2. Generally, we chose the standard basis 0, 1, 1, 0, 0, 1. And we call these spaces the vector 0 and the vector 1. And this notation comes from computer science that uses Boolean algebra to represent a bit using the symbols 0 and 1. Okay. We have to be very careful here because this is not the 0 vector. Okay, this is a vector, a unitary vector. Generally, to represent the 0 vector, we do not use the cat notation. We just use 0 or boldface 0. Okay, but this is already standard in quantum information, and it comes from computer science and Boolean algebra. Okay, but what the quantum bit has, the special characteristic that it has when compared to the classical bit is that the classical bit has two states, 0 and 1. We have the extremal states associated with these bases here, but we can also make superpositions of these states. So here we have a superposition of 0 and 1. And in mathematics, it translates to a linear combination. Okay, so In physics, we talk about superpositions. In mathematics, it's represented as a linear combination of the two vectors. Okay? Questions so far? Okay.
I have a question, but it's more like it's not a doubt, it's just a question. So alpha and beta can be any complex number, but they are on a uh, they are the product of the complex C2 space with something, right? Because the
I didn't
C2, the
understand.
two comes from the two elements of the vector.
Yes.
Yeah, so it's complex on the vector and complex on the coefficients.
No, the vector is complex because its coefficients are complex.
Okay, I get it.
So it's just a vector. It's just like a matrix
Mm-hmm.
two by one with two entries that are complex.
Okay.
So I imagine that you're thinking about this thing here, right? Because you're making the product of a complex number with another vector that could be complex. Yeah, it will in the end give you two complex numbers anyway, but here is even simpler. Let me just set the page here. It's even simpler because these vectors, oh, this is zero is 1, 0, and 1 is 0, 1. So when you make this combination, because these guys are form the uh, standard basis, this will be this and this, which will give you just alpha and beta. I could use a different basis. It will not be that simple, but it would give you two complex number anyway. So it doesn't make any difference. So you can think of a 2 by 1 matrix with two complex entries. Okay? Okay. One of the big deals in that has an intersection with quantum information is uh, the field of quantum foundations that is known today, which asks questions about the nature of all the things that we are dealing with. So in quantum information, one of the important things is to think about applications, protocols, computation, cryptography, really, really applied stuff. But inside the field of quantum information, we have a lot of people also working with the foundations of quantum physics. So every conference or everything you're doing in quantum information, you always stumble upon interpretations of quantum theory. So you, even if you don't care about that much, you will always stumble upon it. So I would like, and also I think for uh, our purposes here, I would like to make clear what is my view of all of the things that I am introducing now. So I would like to make like a brief note about the meaning of the state vector as I see it. It's not the only interpretation that you have, but it's the one I will use most of the time. And you don't need to agree with me. You will be wrong, but you don't need to agree with me. And it's not necessary for anything that we are doing here. But I think it is good that you know my position on this war of interpretations. So there is a big discussion surrounding the meaning of the state vector in quantum physics. And this is one of the greatest debates on the history of physics, and it is far from being settled. And although we had a lot of progress, we will go into that a little bit later on our course, but now just like a small note on it. And what is the way I'll approach the quantum state in this course? It is just a mathematical entity that describes the quantum systems and how we interact with it, the outcomes that we get when we interact with it. And this will give us the information we need, that is the information we can get that is generally probabilistic, and that's it. But there is a controversy in what this state vector really represents and what its nature is. Because when you talk about several things in classical physics, for example, if you talk about position, velocity, temperature, they are things that you can actually feel with your senses. And this is not the same thing when we talk about quantum systems. And it's also not true for some classical systems as well, but in classical physics, we tend to ignore that. But in quantum physics, you cannot ignore that because of the postulates, what the postulates tell you. So the main question is whether the state vector is many options. The main two, an objective description of physical reality, like the state vector is something real and a complete representation of the state of the particle or quantum system. So it's something that exists in nature, whatever this means. And the other option is that the state vector is a representation of our knowledge or our information about that system. So the state vector describes our knowledge of the system's properties, and this is my view of the thing. Okay, so whenever I talk about anything here, I think about all of these objects as mathematical descriptions that allow me uh, to study something, what I know about something. Okay. There are other interpretations that propose something even different from that. So they propose like distinct meanings, moving away from these like purely objective or purely epistemic, that it's based on knowledge. But I will not go into the details here. Okay, so there is like a zoo of different interpretations, and they all give the same practical results, but they assume different meanings for the mathematical objects that we use. Okay? Okay, why do I well, this is actually not just a view for the course itself because it's practical, but it's actually the way I see things. I believe that it's impossible to answer the question what is real or what is not real, because you cannot say anything about reality. You can only say things about the way you interact with other stuff in the world. And science is basically a way of um, formalizing these interactions and having a common uh, way of talking about these interactions. Right? So I think the same question applies to other classical system as well. Well, the magnetic field, the electric field, are they real or they are just a representation of our interaction with a system? So this kind of question also applies to that. So this is the way I see things. And if you're interested, you can study about the other interpretations, but this is the one I will use here. Okay? Questions? So this is really deep, really philosophical. I do not want to go into super details here. Okay? And but I just wanted to make this note. So um, I think it will be easier for you to understand the way I talk about things. Okay, so now we have a mathematical object to describe the state of the system. Now we need a mathematical object to describe our interactions and how we get information about the system. And this is what we call a measurement. So the mathematical object that represents a measurement on a quantum system is an Hermitian operator. So you can think about a matrix, a square matrix acting on the Hilbert space of that system. And this matrix is Hermitian, which means that, so here, Hermitian means that A dagger is equal to A. And this thing here is the transpose conjugate. So you transpose the matrix and take the conjugate of every entry. And this type of matrix, if you remember, they have two special properties. They have real eigenvalues, and they have a basis for the Hilbert space formed by eigenvectors of A. Okay, so let me talk about a little bit about this. Okay, so we have a Hermitian operator A in CD. And we have a list of eigenvectors, eigenvalues. Lambda 1 through lambda d. I will not suppose that they are all different. They could be like, that could be degeneracy. And we have associated eigenvectors. So this means that A view I is equal to lambda I di. These guys are real. And it is possible to choose the vectors vi such that the set of these vectors is an or normal basis. So when you get different eigenvalues, this is automatic. They come out of the diagonalization process. But if you have degeneracy, you have to work a little bit on the degenerate space. Okay, but it's always possible. And when we're studying quantum physics, for those of you who studied physics one in undergrad or later in grad school, you will remember that we pay a lot of attention to these guys here because they are actually the values that you can get in a measurement. They have important physical significance. So for example, if A is the energy, is the Hamiltonian of the system, the lambdas are the possible energies of that system. So the differences between the lambdas are the differences in the energy levels. And this is really, really important when you're studying that system. When we are talking about quantum information protocols and this kind of thing, the actual value of the lambdas is not that important. Of course, then you want to take these things to the lab, you need the actual values. But when you're devising the protocols, that's not really important. The only thing that is important is if they are different or if they're equal. Because here we are talking about information, and information is about distinguishing symbols or outcomes. So the actual value of the lambdas, it's not going to play a major role for us here. So you will see that I would just completely ignore the value of the lambda, and I'll just, for me, the only important thing is the different, how many different values I have. Okay. So in many situations, for us, the actual values of lambda I are not so important for now. Okay. Again, of course, if you go to the lab and you try to implement those things, it is really, really important. Um, for example, if you're building a quantum computer with superconducting qubits, these lambdas are the energy levels of your superconducting qubit. And you have to engineer these levels in order for you to interact with the qubits and in order to connect the qubits with the surrounding qubits and to avoid errors. So it is crucial. But for the protocols, it is not that important. So you'll see that I'll just ignore that in many situations. This is one important thing. Okay. So there are many ways of representing this measurement. So the way we learn in quantum physics courses is through the Hermitian operator. But the important thing for me here is that I'm breaking the Hilbert space into these bases here, which will give me subspaces for each eigenvalue. So let AI be the subspace, the eigen and space of lambda I, and pi the projector onto AI. Okay. So I know that the AI, if I take them all together, they will span H, the H, the Hilbert space. And if I sum all of these projectors, the different ones, because here I imagine that I could have like the equal, it's a bit messy here, so I'll start again. Um, they will sum to the identity. So there are many ways in which I can talk about a measurement.